right, guys, in the last lab, you probably experienced an EPA method. It was a very basic EPA method, and it was just like, hey, let's use a pH meter and measure some pH values of some soil samples that we brought into the house. And the reason we did that, of course, is because soil is a solid, and you might have seen a pH meter and pH theory back in 114, which is our wet laboratory technique course, but we never brought in solids. It was always like, here's a liquid, let's measure a pH. Woo, here's another liquid, let's measure another pH. Well, in that particular scenario, it was a way that we could bring in something that was not a liquid and it was a solid for you. So you understand how these solids can actually work and be okay in a laboratory environment. But it was also a way that we could introduce an EPA formal method to you, so that way you could see kind of how the method originates. So where's the starting point? And then from that, a laboratory would take that method and then they would modify it and they would change it and they would create their own SOPs that you would have to follow in-house. All right, well, we're going to follow that up, and we're going to do, more EPA methods. Woo-hoo-hoo! All right, so with these particular EPA methods, what we're going to be focused on are actually three different ones. It is 160.1, 160.2, and 160.3. We're going to group all of these together for a reason, and you'll see that a little bit later on when we start talking about them, but they are related in some form or fashion. So this video is only going to focus on 160.1, that is it, and it's going to give us some time to really flesh out this method. What are we trying to do in the method? What is this all about? And why is it important? So up at the very top, I see method number 160.1, and then over here to the side, it says a residue filterable. All right, woo, look at me. I use fancy words to describe a method. No one really calls this filterable residue, folks. No one really says this at all. We go by a different kind of term that we like to use with this method, and it's a little bit of lingo, but at the same time, I mean, I'm going to kind of tell you how we refer to this as, because that's what most people do in real life. They're never calling it residue filterable. I'm going to do my residue filterable method. No, that's not really what goes on. Okay, either way, it says residue, comma, filterable, and it says gravimetric, comma, dried at 180 degrees Celsius. So it tells me up at the very top, instrumentation that's going to be needed. Oh gosh, it's going to break the bank. It's just a drying oven. That is it for the most part. That's the only type of equipment that I need. Now, of course, lab supplies and stuff are different, but instrumentation wise, we're sitting pretty. I mean, we've got drying ovens in the lab. I mean, I hope we do at least. Otherwise, what kind of lab do we have? All right, so I'm going to tell you a little bit of a rundown of what this method is all about. So let's say that you go into your kitchen, and then here I've got a big old pot of water on the stove top, and I'm getting ready to boil spaghetti noodles. Okay, so I'll look at all the cooking shows, and they're going to say, oh, well, Tracy, if you want a really good noodle, then you're going to put in sodium chloride into that water, and that way it will flavor your noodle, and it's all about building flavors, one ingredient at a time. Okay, so I'm going to add sodium chloride into that water, and I'm going to stir it up, and what's going to happen, folks? Of course, right? It's going to dissolve. All right, so that's good. So I've got this water, and it's heated, and it's dissolved the salt, and it's going to be salty like the ocean. And then I always look at how much salt that they add in those cooking shows, and it's like a whole handful, and then it gets me anxious, and it gets me nervous. But, okay, I'll follow it. Okay, either way, what I'm trying to get around to is the idea that things dissolve in water. That's what this is all about. So if I took a portion of this water sample, and let's say that I filtered that water sample, okay, that's great. The water is going to go through. So I've got a container down here at the bottom of that filter. So that water is going to go through. Absolutely it will, right? The salt is dissolved. And it's dissolved fairly well. And that means that if the water goes through, there is a very strong chance that the filter paper, depending on the type that I use, let me make that very clear, because there's tons of different types of filter papers. But depending on the type of filter paper that I use, that dissolved salt will actually go through as well. That is a thing. Okay, nothing's going to be held back. Nothing's going to be on the filter paper itself. what will be on the filter paper will be like chunks of stuff if I didn't clean out my pans. So if I'm a nasty cook and if I don't like to wash dishes, well, there's probably gunk and nasty things floating around, and I hope you don't invite me over for dinner if that's the way that you do stuff. But those visual things that I see with my eyeballs, those are not dissolved. That is not what we're talking about here. When this method says residue that is filterable, that means it is stuff that goes through the filter paper. So I am not looking at all of the gunk that's up here on the filter paper. All of this stuff, if there is stuff there, all of this stuff, I'm not looking at that in 160.1. I am looking at the stuff that made it through the filter paper. So we are going to filter our samples in this method. When we filter the samples, some of our stuff is going to go through the filter paper along with the water, because that's what we're going to be using. And then anything that has been dissolved in that water sample will also go through that filter paper as well. That is what we call filterable residue, because what will happen after the fact, after I filter this, and once we do what the method tells us to do, then what will happen is that we will evaporate the water sample. And when we evaporate the water sample, we will be left with residue that will be in that container at the very end. So I want you to think of, again, outside in like your yards on a hot summer day, you could have a little kiddie pool or whatever the case might be, and you fill it full of water. Okay, so during the summer, hot summer days, that sun is going to generate a lot of heat. Woo! It's 110 degrees out in Wilmington. And then all of that water is going to evaporate. Slowly but surely it will evaporate. Slowly but surely, yeah, that's right. It's going to require a little bit of patience with this method, but that water is going to evaporate and you'll be left with like a little crust. You'll be left with some residue. Folks, that's what the residue is talking about in this specific method. All right, so filterable residue, we do not call it that most of the time. So these are dissolved, okay? So this is dissolved stuff that we are using in the method that we want to focus on. And for that reason, we will often call this TDS. And the T is going to stand for total. The D is going to stand for dissolved. And the S is going to stand for solids. And the reason we use solids is because most of the time when we evaporate this water off, that residue will be a solid residue that is left behind. So for instance, if I took my spaghetti water and I evaporated all of the water off and I leave it on the stovetop to do that, I mean, that's okay. What I will be left behind with is some salt crust that will be inside of my pan. That is going to be the focus of method 160.1. Anything dissolved in the water sample that will make its presence known after the water gets evaporated off. All right, so let's take a look at section 1 of the actual proper method. It says scope and application. This method is applicable to drinking, surface, and saline waters, domestic and industrial waste. Whoa, gosh, I hope I can stay away from the industrial waste. I mean, is that like fecal matter and poop and stuff? Okay, well, as long as the sample fits into one of these categories, we can use this method 160.1 to process those samples with. So it looks like drinking water is going to be okay. So that's going to be, of course, the stuff from your tap, and you can catch it into a container, bring it into the lab, and do method 160.1 on it. And then all of the other options of those water types are going to be listed for you in the method. And if it doesn't fall into one of those categories, folks, method 161 is not going to be applicable for what you need. 1.2 says the practical range of the determination is 10 milligram per liter to 20,000 milligrams per liter. Oh my goodness. All right, so what this means, well, milligram per liter is a great unit to kind of talk about, but you're going to see a shorthanded, in a way, roundabout way, way of stating milligram per liter, and we often call this part per million. So that is a ppm. And look, that is such chicken. I'm going to actually rewrite that one myself. Okay, so ppm. ppm means parts per million. That is what that represents. And parts per million is a very common unit in an analytical laboratory. So this method is telling me, okay, if I've got a water sample and I bring that water sample in and I filter it and I get this residue in the very end, if my numbers go anywhere between 10 part per million all the way to 20,000 part per million, then folks, this is an accepted method. So this is a extremely wide range of values that this method is approved from. Now, here's the kicker. If my samples go lower than 10, or if it goes higher than 20,000, this method is probably not going to be approved for you formally, and you're going to have to make measures to make sure that you are doing the test the right way, you're generating data the right way. Is there something else better that can be out there that can go lower than 10 or higher than 20,000? But the way that this method is written, unless the laboratory can show otherwise, this is really going to be for the range of 10 to 20,000 ppm, or 10 to 20,000 milligrams per liter. So what this means, if you want to think about this visually, is let's say I go to the grocery store and I get a 2 liter of soda. Okay, so take that 2 liter of soda and cut it in half. That is 1 liter. All right. So if I have that 1 liter and I evaporate all of that water off from that 1 liter, I can have 10 measly little milligrams of residue that could be present. And this method would be approved for that. Or I could have 20,000 milligrams of residue that is left behind. And folks, 20,000 milligrams is quite a bit of stuff. So for the most part, this will work for most of the samples that are submitted to the laboratory. Now, if I am using something like water for injection, all right, so water for injection is a term that's used kind of in the pharmaceutical industry. And this is very super clean water that they have to use for like liquid injections and stuff, right? So they want to make sure that they are not injecting you with stuff that's going to set up some type of infection. And this water for injection has to be the cleanest of the clean. Well, this is probably not going to work for that because I will not have 10 milligrams, I hope, of residue that is there. I would hope that my stuff is completely clean. Either way, it gives me a range to work with, and that's the range that we'll go by. Section 2 says summary of the method. A well-mixed sample. All right, so that means when I get the sample in the lab, I'm going to well mix it. Okay, so I'm going to shake it up, right? If stuff has settled to the bottom, then I'll really want this to be a representative sample. So if a sample is given to me and a sample has settled out in the bottom, I am not just going to pour the little bitty tiny little bit on top and leave all of the other stuff behind. That is not representative. It has settled out. It doesn't look the same from when I've gathered it. So what I need to do is that I need to mix it really well before I use it. So shake, 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 shake your bottle, woo, woo, shake your bottle, woo, woo. All right, so that's what I need to do here. We're going to filter it through a standard glass fiber filter. All right, so glass fiber filters are probably something that you have not actually encountered before in our lab, and I'm going to show you what these glass fiber filters look like. So over here to the side, I'm going to write, hey, hold up, people. The type of filter paper that we are going to be using this time is not our regular filter paper. Alert, alert, alert. It's not the regular filter paper that we're going to be using. We need something that's called a glass fiber filter. The glass fiber filter actually has larger pores and more stuff can go through the glass fiber filters. And that's kind of the point of using them, because anything dissolved, we want to make sure that it does go through, and we only want that filter paper to keep some larger stuff that's behind. So if I can see this visually with my eyes, then that is the stuff that's going to be kept behind on that glass fiber filter. And I want the majority of that sample to go through, but those dissolved solids, folks, they need to go through that filter paper. And if we choose the wrong filter paper here with smaller pore sizes, then this method is no good anymore, because we are not following this method as it is written and as it is intended. So it looks like I'm going to filter stuff through, and then it says the filtrate is evaporated. Woo! What is filtrate? Okay, so filtrate is the stuff that has been filtered. So all of the things that I'm collecting in that beaker at the very bottom, that stuff is my filtrate. That has made it through the filter paper. I'm collecting it, and then that filtrate is going to be dried to a constant weight at 100, whoa, that's hot, 180 degrees Celsius. Most of the time, our ovens are set at 105 to 110, and the reason we do this is because that dries our glassware pretty well. 180 is hot, so make sure that you're picking the right oven today when you make it to this point of the method, because things are going to have to be evaporated, and 105 to 110, it's going to take forever. So we need a hotter oven in order to do this, and that's where that will end up going. So double check your oven temperatures. Make sure you're picking the right one when you place your containers in there for method 160.1. 2.2 says if residue non-filterable. Oh, tricky. What do they have here? If residue non-filterable is being determined, the filtrate from that method may be used for residue filterable. So we are going to talk about this, and this is a different method, and we're actually going to be doing two methods at one time in a way, and I'll kind of mention this a little bit later on down the road, but again, we're going to go do these in order. So 160.1 is the one that we're going to first talk about. All right, so we'll come back to that. Number 3 says definitions. Filterable residue is defined as solids that are capable of passing through the glass fiber filter. So we talked about this already. That's great. I have this idea of what's happening now. Section 4 says sample handling and preservation. 4.1 says preservation of the sample is not practical. Analysis should begin as soon as possible. Refrigeration or icing to 4 degrees Celsius, which will minimize microbiological decomposition of the solids, is recommended. So this kind of means if I'm going out and I'm collecting water samples, if I know it's going to be a while before I make it back to the lab, then I need to keep these samples cold. And I need to keep the samples cold, not because it's destroying the residue that might be there, but I want to minimize what they call the microbiology aspect of things. So I don't want any of that stuff kind of taking over and then eating or breaking down anything that might be in the sample to destroy it in any form or fashion. So with that said, if I'm out there collecting samples, bringing them back, I might be required to place them into a cooler, keep them cold. 4 degrees Celsius, this is the typical temperature of a refrigerator. So that is normally what we are operating at. So at least keep them cold until they make them back to the lab. And then when it gets back to the lab, it tells me in this method, like I should be filtering these as soon as possible. And it doesn't take a lot of effort to do this. It just requires some filtration here. So I should not be placing these off to the side of the countertop. I should not be waiting days and days and days before I get to these samples and then go to the sample that's been sitting out for days and then begin method 160.1. That is not how I should be handling this. If I cannot get to it immediately in the lab, then of course I need to place those samples in the refrigerator until I can get to them, but I need to get to them as quickly as possible. That is what this method states. So don't be lazy, don't bottle up, don't have a line of samples that are waiting for filtration that will take days and days and days. You need to filter these as quickly as possible, and that's one of the reasons, so we do not violate the method. Section 5 is interferences. Highly mineralized waters containing significant concentrations of calcium, magnesium, chloride, and or sulfate may be hygroscopic and will require prolonged drying, desiccation, and rapid weighing. So the thing here is that it was kind of strange. Highly mineralized. Well, this could actually be some people's tap water, right? It doesn't have to be specialized water here. Depending on the area of the country that you're living in, you might have extremely hard water. And hard water, if you were part of our CTC 114 class, you did a water hardness titration. And that water hardness titration focused on the amount of calcium and magnesium that's swimming around in your water samples. So what this interference is basically telling you is like, hey, heads up! If you've got a water sample and it has a really high level of calcium or magnesium or chloride, why would it have chloride? Well, again, tap water, they're chlorinating your stuff by the time they send it to you tap water. I mean, they're going to try to kill out bacteria and other nasty stuff before they send it out to your tap. So chlorination and bromination is pretty common. So that's kind of how chloride would be there, or high salt content. So this is something that we've got to deal with. And it says, listen, you might just have to kind of heat them a little bit longer. Just be more patient with them. 5.2 says samples containing high concentrations of bicarbonate will require careful and possibly prolonged drying at 180. So once more, it is like, okay, this is not a drastically huge deal. You just need to go into this knowing that your heating process is going to take a little bit longer. So we're okay with that. We just got to be patient. And then 5.3 says too much residue in the evaporating dish will crust over and entrap water that will not be driven off during the drying. So total residue should be limited to 200 milligrams. That is really what they're after here. So what this means, okay, you're going to be like, whoa, wait a minute. I thought that you could go from 10 to 20,000. Well, you can. You can go from 10 to 20,000. That is not a big deal. But it's 10 to 20,000 milligrams per liter of stuff. And what this is trying to tell you is, listen, you are not going to be filtering a liter of stuff. You are going to be taking an aliquot of that sample, which just means a portion. You are not filtering a liter. You will be filtering a portion of that liter or that sample that's provided to the lab. So that portion that you are filtering, you should not have any more than 200 milligrams of residue that is staying behind. If you do, then what's happening here is that toward the end of this, there will be so much solid that it will somewhat form a layer over the water that needs to evaporate off. And that surface, it's like an ice over a frozen lake, right? So that surface is going to be very hard to break, and we don't want that risk to happen. So what this is basically saying is, okay, if you have a water sample and there's a lot of residue in that sample, you need to be very careful. The portion size that you use and that you filter, you want to make sure that that portion size does not give you more than 200 milligrams in total. Because if it does, then what will happen is that your little water lake is going to be, in a way, frozen over. It's going to have this crust layer on the top of all of the residue that has formed, and water is going to be trapped underneath it. And if water's trapped underneath it and it cannot get out, it cannot evaporate. And that skews the results, because the whole idea here is to get rid of all of the water in the very last steps. All right. Section 6 says apparatus. Section 6.1 says glass fiber filter disc, 4.7 centimeters or 2.1 centimeters without an organic binder, Reeve Angel type 634-AH, Gelman type A/E or equivalent. Oh my goodness. Folks, this is how specific the method can be. So it is telling you you need glass fiber filters, and these are the two dimensions that you are allowed to use. And this is basically the one that we recommend. And if you don't want to use those, then you can use something that your lab deems appropriate, but you have to prove that it is equivalent to these. So that means if I don't use a 4.7 or a 2.1 centimeter size, I am violating the method, and I cannot do that. So when I order these materials and when I order these supplies in the lab, I want to make sure that I am ordering the appropriate stuff. And those are the only two sizes that are going to be allowed. So think of these as the diameter of the filter paper, 4.7 centimeters or 2.1 centimeters wide or in diameter, without organic binder. So maybe there's a version out there that's got organic binder. When I order this material, I've got to make sure that it doesn't have that organic binder because it specifically says it here. And if I'm weirded out about it in any certain way, then they're giving me an option to say, hey, this is what we recommend. If you have no clue what you're doing, this is what we're going to say to go with, and this will maybe make your decision a little bit easier. Next up is a filter holder, and it says membrane filter, funnel, or Gooch crucible adapter. So we need to talk about these filter holders. This is very loose. As long as it is suitable to hold the filter, then you will be okay. That is not an issue. So filter holder is great. We just need to make sure that what we have will actually be appropriate for the size of filter that we are using. 6.3 says a suction flask, and a suction flask says 500 milliliters. All right, so a suction flask is like an Erlenmeyer flask here that's got one of these side arms on it. And this side arm is going to be connected to some type of aspirator or some type of pump. And what's happening is that it's creating some suction. So on top of this side arm or suction flask, we're going to have the piece that's going to be holding the filter paper. And then I'm going to be pouring my water sample through that funnel or that filter paper, and it's going to be sucking that water through so I don't wait forever, and it's going to be allowing that water and the dissolved residue to flow through that glass filter, fiber filter, and we can kind of do what we need to do after that fact. But that is what a suction flask is. And notice it says 500 mils. That is what they recommend. That's what we should be using. 6.4 says Gooch crucibles, 25 milliliters, if 2.1 centimeter filter is used. So the 2.1 centimeter filter, this is a much smaller filter as far as size goes. And a lot of these types of funnels that you'll see here on the top of the sidearm flask, they're going to be quite larger. So if you use the smaller filter paper, that's fine, but you probably need to use a Gooch crucible instead of one of these regular types of filters or filtration setups that we're going to be using in our lab today. So keep that in mind. Again, we're going to use the 4.7 in our lab, and therefore we're going to be using the regular filter setup, and we're not going to be using the Gooch here. 6.5 says evaporating dishes. You want porcelain evaporating dishes, and it says 100 mils in volume. And it gives me some options. It's like, okay, if you don't want porcelain, then, you know, these two materials are going to be okay as well. I mean, that is perfectly fine. If you have those in house, use them. Porcelain very often is going to be pretty common. It is tending to be one of the cheaper types of materials that we can use for our crucibles, our evaporating dishes. And that's what we're going to be using in our lab experiment with 160.1 anyway. So those evaporating dishes we're going to pull out. They do hold 100 mils, so they're going to be a little bit larger. They can come in different sizes, as you can imagine, so you want to make sure that you pick out the appropriate size for our method. 6.6 says a steam bath. All right, so there's a steam bath. A steam bath is basically just a water bath, and the steam is a little bit hotter, and the steam is going to hit the evaporating dishes, and that steam is going to help drive off that water a little bit faster than if you just placed the crucible or the evaporating dish on the surface of a hot plate. All right, so a steam bath is basically this idea that I've got a hot plate here, I've got some water, and that water is it's boiling, right? So the steam that is coming off from here is a little bit hotter. So I'm going to erase this flask up here at the very top just for a minute. Here we go. Oh my gosh, he's slowed down and he's talking like normal. All right, so here is our steam bath or our hot water bath. bath. And then normally kind of what happens is that I can put an evaporating dish right up here, and that steam is going to come in contact with that evaporating dish. And when it does, all of the water sample that is going to be in my evaporating dish will be able to evaporate and will go away much, much faster. That is much safer than scorching my sample. All right. So think about like melting chocolate in a kitchen. If you were melting chocolate, you don't put the chocolate chips in a pan and put the pan on the stove eye. That is not what you do, because you have a chance of scorching the chocolate, and no one wants to eat scorched chocolate. They might look at you and say, "Oh, this is the best dessert ever. Oh, yum, 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 yum." And they've just got manners and they don't want to hurt your feelings, and they don't want you to tell you that you got scorched chocolate. So instead, you always put it over a double boiler, right? You've got a hot water bath going on, and then you put a bowl on top of the pan, and then you put the chips in the bowl, and the hot water or the steam that's coming from that stove eye is hitting your chocolate chips, and it is melting those chocolate chips, and it is making sure that you do not accidentally scorch the stuff that you're working with. The same thing's happening here. We don't want to scorch the residue. We want to make sure the residue stays behind, but we want that residue to be the residue. We don't want it to be burnt crisp. So that is the purpose of the steam bath. And that is why we do not put these directly on the hot plate. Next up, the drying oven, and it says the drying oven should be set at 180 plus or minus 2 degrees Celsius. All right, so that means I'm going to go to my oven. I'm going to make sure that I've got it at 180, but I want to make sure that this threshold, folks, is actually kind of being tracked and monitored. So that means that as a laboratory person, I might be required to log the temperatures of the oven over the course of a day. So there is a reason for that. And that's because some of these methods are very specific. And if my oven cannot maintain plus or minus 2 degrees, I violate the method as it's written. So I've got to make sure that I have an oven that can maintain constant temperature. So throughout the day, there's probably going to be a little logbook. And throughout the day, I might be required to go over to the logbook and write down the temperature of that oven at that moment in time. Now, sometimes these logs can be done manual, and that is me doing the job, or it can be done in some type of automation type of system. So I can get a temperature sensor, and that temperature sensor can constantly maintain the temperature throughout the course of a day. And then that temperature is going to be sent to some type of computer software that is logging that information over the course of a day. And then day after day after day after day, it will save it. The reason that that is important is not to drive you crazy, but it's because the method specifically says plus or minus 2 degrees. And if I go outside of that window, or if my oven cannot hold and constantly maintain that temperature as that is, then I get an issue. And that issue is that I'm violating the method. So an auditor might want to see that kind of information, and that's bad if I cannot generate that to an auditor. Next up is a desiccator. So the purpose of the desiccator is to keep things dry. What happens here is that if I'm evaporating this water off and I've got this residue crust that is left behind, then the desiccator is going to be used to place that evaporating dish on the inside, and it will help keep that evaporating dish dry. The desiccator's purpose is not too dry. That is not why we do that. That is not going to go on. It already has to basically be dry before we put it in the desiccator. So the desiccator is going to prevent any outside moisture, maybe in our room, to latch onto that residue and to increase our weights, and for that residue to grab out to some of that water and hold on to it and basically turn back into a liquid. We don't want any of that kind of stuff to happen. So we put it into a closed chamber, and that closed chamber is going to be called a desiccator, and it prevents a lot of that water moisture from encountering our residue that hopefully has been fully dried at this point. All right. So in other words, you can't just put a glass of water into a desiccator and think that that desiccator is going to be able to fully dry out all of that water and capture all of that water. That is not how desiccators work, and nor is that their purpose. And then finally, 6.9 says analytical balance. And it says capable of weighing 0.1 milligram. Whoa, gosh, what is that number? All right, so 0.1 milligram. Milli means 3. All right, so if I go over 1, there's 1, and then 2, there's 2, and then 3 is where that decimal is going to go. So what this means is that you need to use balances that can record data with 4 digits after the decimal point. So this means that if I'm in the laboratory and I'm doing work and my lab only has numbers that can go to 3 digits after the decimal, that is not an approved balance for this method. I cannot use those. I need balances that go to 4 digits because that's what this method says. You've got to be able to weigh 0.1 milligrams in the laboratory setting because these numbers can be very small. And I want to make sure that if I'm getting these small values, that my balance is capable enough of seeing them and that they are that sensitive. So folks, you might not like the balances that have the 4 digits on them, but those are much better balances, even though they take a while to stabilize, even though they take a while to do their job. And you're like, gosh, this is the worst balance ever. I hate these. Where's those other ones? Well, the reason it's doing that is because it's so sensitive, because it can go lower in the mass measurement and it takes them a little bit to stabilize out. So again, be patient. That is the moral of the story. All right. So that's going to lead us up to section 7, which is the procedure. In the next video, we're going to talk about method 160.1 procedure-wise in order to figure out what I need to do on my end to process a sample here the proper way. So that's going to take care of every material, piece of equipment, supply, things to know going into this method. So that way I kind of have a general understanding of what's getting ready to happen. And then in the next video, we'll talk about the individual procedure steps. So come back and see me. I'm going to talk about these. These are important. And then from that moment on, we'll kind of keep trucking.